take a look at that little paragraph right there, and let's see if we can fill in what we've got here. So we've been learning about functions in Chapter 1, and we've reviewed the idea that functions are very, and I'm going to use this word, they're very consistent mathematical rules. And what they do is they take any number that we plug into the function, or sometimes we've even plugged in some ugly looking expressions, okay? So any number or expression that we plug in, okay, it's going to perform some math on it, for lack of a better word. This isn't very mathematical, but it does get the idea, right? We plug something in and it does some math on it. Maybe it squares it, maybe it divides, by 7 or something like that. And then it gives you an answer, okay? Well, it turns out once we know how to work with basic functions, once we've got the basic idea of how functions work, okay, we can add them, we can subtract them, multiply and divide them, and we're going to get some new, probably more complicated functions. Okay? The only thing that we need to be careful of when we're adding, subtracting, multiplying, or dividing is we've got to be careful when we do division. Okay? Got to be careful that we haven't introduced any domain issues. Okay? So domain's going to be a big deal with these. So literally, some of the problems that you're going to do are this easy. They'll give you a function, nice simple function that we already know how to work with, square root function. We know what shape that makes. And this function right here, which is a linear equation. So we've got a square root graph and we've got a linear equation, and we put those together. Okay? And literally, we just add those together. So f plus g would be the square root of x, because that's f plus, and I could put this in parentheses and then simplify. Okay, addition's pretty darn easy, but that's the answer. That's what you get when you add those two functions together. Now, if I'm going to write down what I get when I do f minus g, square root x, minus, it's a big deal on this one to put that in parentheses because I'm subtracting every term in that second function. So this is going to be the square root of x minus 2x plus 8. That's that new function. And this is just a multiplication problem, so we'll just do square root x, 2x minus 8. And really there's not a bunch of simplification that you do there. And then f divided by g would be the square root of x divided by 2x minus 8. Okay, so there are 4 new functions created from 2 very simple functions, f and g. Okay, pretty easy, right? Okay, now let's come back and let's talk about the domain. So I'm going to change colors here, and let's think about the domain. Okay, can you plug anything you want into this one? Yep, the domain for this one is all real, so it's negative infinity to infinity. What about this one right here? What about the square root function? Just 0 and forward, right? Okay, now, when you put 2 functions together to figure out what the domain is going to be at least as small as the smallest of the 2 domains, maybe even smaller. So which of these 2 is smaller? From 0 to infinity or from negative infinity to infinity? 0 to infinity, okay? So the domain on this one is going to be from 0 to infinity. And it would be a good idea just to double check and make sure. I'm not plugging anything into the 8. Anything I want is okay to plug into 2x. And the square root function, I've got to make sure I'm plugging in non-negatives, or in other words, 0 to infinity. So of these 3 terms, which one restricts the domain the most? The square root does. Okay? That make sense? Okay. What about this one right here? Same thing. Okay. The domain on this one's going to be from 0 to infinity. What about this one? Cameron? Same thing. From 0 to infinity. And then let's look at this last one. Every one of these had exactly the same domain. It was the square root function that restricted the domain down from 0 to infinity. But let's look here. It certainly can't be any bigger than this. Okay, so I know it's got to be at least that small, if not smaller. Is there anything else that I ought to be concerned with here? Logan? X can't equal 4. By dividing these two functions, I've introduced another domain issue. Okay, I need to make sure that the denominator is not equal to 0. And what would make that equal to 0? 4 would. So in addition to restricting it to just 0 to infinity, I'm also going to have to throw out the number 4. So when I say it's at least as small as the smallest of the two, the smallest of the two is from 0 to infinity, I have to throw out an extra number because of the operation that I'm doing here. I'm doing division. Okay? Just for the heck of it, what would happen if I did G divided by F? What if I did G divided by F? So let me change colors again. What one would be on the top now? Okay, 2x minus 8, and the square root would be on the bottom. Can I do this for the domain? I see some shaking heads. Somebody tell me why. Why can't I do from 0 to infinity? Sven? Okay, so we can't plug in a 0 now because we're dividing by the square root of x. If I plugged in a 0, I'd get the square root of 0 on the bottom, which is 0. Can't divide by 0. So what I'd have to do to change this is just make that a round bracket rather than a square one. And notice that 4 is okay now because I don't have that expression 2x minus 8 in the denominator. Any questions? Okay, so those are some pretty simple problems there. Let's take a look here. Let's do f minus g. Here are a couple functions right here. There's f, there's g, there's h. And then it says, find the following and state the domain. Usually it's not very difficult to figure out what the new function is. So this is going to be 3x plus 4 minus, and I'd be careful with that, x squared minus 3x plus 1. If you can do the work and just write down what it is, let's see, this is 3x plus 4 minus x squared plus 3x minus 1. We're just distributing through and collecting like terms, right? So I've got a minus x squared. I've got a 3x and a 3x, so that's going to be 6x. And then I've got a 4 minus a 1, so that's going to be plus 3. So this right here is what we get when we put the two of those together. What's the domain for both of these? Negative infinity to infinity on this one, negative infinity to infinity on this one. Okay? So the domain for the difference between the two of those, the new function that we made, is at least as small as the smallest one. Okay? Have we introduced any new domain issues? Do we need to be careful with anything? Nope. Haven't introduced division or anything weird like that. So the domain is going to be from negative infinity to infinity. Okay? Any questions? Okay. While we're at it, take a look at this one right here. What's the domain for this one? Raymond? Okay. Everything except for 3. Okay. Now, let's find this new rule right here, or this new function. Let's do f divided by h. So f divided by h would be this one right here. So this is going to be 3x plus 4 divided by h. H is x over x minus 3. Boy, that does not look like our favorite thing to deal with. Okay, that has a name. Does anybody remember what this is called? Yep. What is it, Tammy? Complex fraction. It's called a complex fraction. Okay, do we ever divide by a fraction? Nope. I'm going to take this, I'm going to flip it over, and I'm going to multiply. So this is going to be x minus 3 over x. So when I multiply those together, here's what I get. I get 3x plus 4 times x minus 3, and then the denominator is x. Okay. If you want to multiply those out, you can. There's not much point to it. Maybe you'd think that would look a little bit better. I think this would actually be easier to work with as it is right here. Now I want to figure out what the domain is. Okay, so write down what you think the domain is, and then check with your neighbor. Remember, it's got to be at least as small as the smallest domain for the pieces that we're using. So we used F and we used H. Okay. Anybody got an answer for us? Anybody want to volunteer their answer for us? Somebody besides Raymond. I call on him all the time. Yes. Okay. So one suggestion is from 0 to infinity with round brackets. Up. Can't equal 3. Sven? Is it louder? Including the negatives. So instead of this, go from negative infinity to infinity, x not equal to 3. Also excluding 0. Okay. Does everybody agree that we need to throw out the 3? Because 3 didn't work in the original function, so it wouldn't work when we put it together with another function. Okay, so everybody agree we need to throw out 3? Okay. The other number that we need to throw out is 0. So the easiest way to figure these out, generally speaking, is throw out anything that doesn't work with either one of the two pieces to begin with. Okay, so what didn't work is the 3. And then simplify your answer and see if there's anything else you need to throw out. In this case, you can see that we're dividing by x, so I can't use a 0 either. So it's from negative infinity to infinity, except for these two numbers, only a 3 and a 0. You can see why we can't plug in a 3, but take a look. If I plug a 0 in right here, I get a 0 on the top and a negative 3 on the bottom. That gives me a 0 down here. Plugging in a 0 makes the denominator equal to 0, even as it's written like this, and definitely when it's written like that. Okay? But again, generally it's just easier to throw out anything that you need to begin with, and then simplify your answer, and then throw out anything else. Okay, any questions there? Okay, that's how we add and subtract, multiply and divide, and figure out the domain. Now we're going to talk about something called composite functions. Okay, raise your hand if you've heard of composite functions before. Okay, a couple of you. Okay, so here's what we want to go over. Okay. Adding, subtracting, multiplying, and dividing those are just a couple of ways that we can combine functions. Another way that happens quite a bit is we do what's called a composite. And a composite is when one function gets plugged into another function. So if we've got a regular function like f, just kind of a generic name for a function, and we plug in x, we get out f of x. But if I plug in g of x into f, then I get f of g of x. Okay? Whoops. Make that a little bit bigger. F of g of x. Okay? Stuff is erasing. Plugged. I'm going to save this. Okay? All right. Sometimes this program, depending on the zoom factor. Okay, so now it's sticking around. That's good. Yeah. Oh. Yeah. There you go. If you come in, just come up and grab one. Okay. But the best thing would be to get here on time, right? Okay. So if we plug g of x into f, we get f of g of x. And there are actually a couple different types of notation for this. I think this is the best because you can kind of see that g of x got plugged into f. Okay? You can also write it this way. You don't say this fog or something like that. You literally say it f of g of x. Okay? The little circle there could stand for the word of, I suppose. Okay, so if I take a look at this diagram over here, this kind of indicates what we're doing. With a normal function, I plug in an x and I get out an f of x. Okay, so if I plug in a 2, plug that in here, and what comes out is f of 2. If I plug in a g, what comes out is f of g of x. Okay, so let's go through and let's do a couple of problems. And a lot of times it's helpful to think of these in terms of an outside and an inside function. So here's h of x, square root of 2x minus 7, okay? And f of x, the square root of x, and g of x, the square root of 2x minus 7, okay? The nice thing about composites, or one reason why we find them so useful, is you can write nearly any function as a composite of two functions, as one function plugged into another function, okay? So this says, write h of x, which is the square root of 2x minus 7, as a composite of these two functions. So what got plugged into what here? 2x minus 7 got plugged into here. All right. That's irritating. I'm going to shut this down, and we're going to open it up again. Okay, so 2x minus 7 got plugged into this right here. So h of x is f of g of x. Because if I do f of g of x, f is the outside, and this is the inside function. We plug the inside function into the outside function. So everybody watch, please. I think it's helpful if you think of it this way. The outside function is the square root function. So we're going to do f of something, and what is that something we're going to plug in? We're going to plug in 2x minus 7. Okay? No need for parentheses on that particular one. So we've got an outside and an inside function. Okay? And then we've got a couple of more typical examples that we'll see. If I've got f of x is 3x and g of x is x squared minus 1, here's what we want to find. We want to find f of g of x, or again, I like writing it this way. So f is 3 times something. 3 times something. What is that something that we're putting in place of the x? G of x. And what is g of x? X squared minus 1. Then we simplify just a little bit. Probably the simplest way to write this would be 3x squared minus 3, although either one would do there. Let's look at this one. This is written backwards, so this would be g of f of x. So what's getting plugged into what here? F is the inside, g is the outside, so f is getting plugged into g. So let's write g. G is something squared minus 1. And what is that something that we're plugging in? F of x, which is 3x. And then we'd clean this up. We'd probably write 9x squared minus 1. And there's g of f of x. Okay? This is kind of interesting. Again, if we write it in the notation that I like, this is f of x. So the outside function is 3 times something. And what are we plugging into it? We're plugging itself into itself, right? So we're plugging 3x into 3x, and I end up with 9x. Okay, would you do the last one, please? Find f of 2. We actually get a number to plug in here. So one way you can figure these out numerically is you can do this. This is f of 2. Well, let's figure out what f of 2 is. F of 2 is 3 times 2, right? So f of 2 is 6. So we want to find out what f of 6 is. And f of 6 would be 3 times whatever you're plugging in, so that's going to be 18. That would be one way to do it. Okay, that would be doing it in pieces. The other way to do it is, don't we have a rule for f of f? Yep. What if we plugged a 2 in here? Don't we get the same thing? Okay, so that's the other way to do it. Okay, now we're going to take a look at finding a composite, and this is usually the hard part. Okay, figuring out what the domain is. Okay, same type of rules apply. Okay, we're going to need to throw out anything that doesn't work to begin with. We're going to find out what the composite is, and then we're going to throw out anything extra. Okay? So we're going to figure out what f of g of x is. So f is a big square root. And what am I plugging into that square root? 3x minus 5. Okay? That is the composite. Now I need to find its domain. So what function did I start with? So let's look at this original, the inside function. Okay, do I need to throw out anything there? Nope, because that domain is all real numbers. Let's look at this right here. Do I need to be careful with even roots? Yes, I do. I need to make sure that this is always greater than or equal to 0. So we'll move this over. 3x greater than or equal to 5, divide by 3. So I get x is greater than or equal to 5/3. I could write it that way as an inequality, or I could write this is 5/3 all the way to infinity. It's all greater than 5/3. Round brackets here. What about the 5/3? Square brackets there. Okay. Any questions? Throw out anything you need to of the inside function, which was this one right here. Anything worked there, so we didn't have to throw anything out. Find the composite, and then throw out whatever doesn't work there. Okay? So we had an even root. We needed to make sure we were taking the even root of a positive. Okay? Any questions? Okay. Go ahead and flip the page over. More practice with these, but these are slightly more complicated. Not much, just slightly. So let's look at these and figure out, first of all, what's the composite, and we want to figure out what the domain is. So we're going to do f of g. So that's f of g of x.